Gerrymandering, Where Do We Draw the Line? By Taylor Boatwright for the Math 499 class with advisor Dr. Dan Scofield. Every 10 years, the government takes a census of the U.S. population. Electoral districts have to be changed to reflect changes in population as districts are set up to have approximately 700,000 people in order to ensure equal representation. Other than this number and the requirement of continuity that the federal government sets in place, state legislatures have very few guidelines to follow. Therefore, each government has their own method of redistricting. This can lead to gerrymandering, which is a practice intended to establish an unfair political advantage for a particular party or group by manipulating district boundaries. This can occur in a few ways. One is packing by grouping the majority of voters for one block into a single district so that they cannot win any others. An example of this is Charlotte. Charlotte is a highly concentrated area of voters for one single party, so it's easy to group or pack it all into one district so that even though for the whole state they are winning overall, they're only actually winning a very few districts. This is very common when looking at other large cities, including on this map Winston-Salem and Greensboro. The second way is called cracking, where you split up all the voters for one party into multiple districts where it is not possible for them to ever have the majority. If you look at the map on the bottom left compared to the map on the bottom right, you can see how just a very small change in that far left district led to a very different result. This is similar to cracking because they're cracking up those voters. And then North Carolina is a very famous example for the different ways it can be manipulated. The images below really show how different and very small changes in the boundaries can affect the district outcomes and the election results. This state is actually a famous example because it went to the Supreme Court to be dealt with in 2018. You can see how the Democratic Party was only winning 3 out of 11 districts in 2016, but for the state as a whole, they held between 60 and 70% of the vote. This disconnect between the percent of the vote and the district or the outcomes of the elections shows how much gerrymandering was taking place. If it were to actually represent the state how it should, then the map at the bottom right would have been the most likely result, but we were not seeing this in real life. Many methods have been created to judge if gerrymanders occur, but there are a few that are more widely accepted. One is looking at the geometric features of a district. We can compare the concavity or the compactness to an accepted value. By looking at the concavity, we can look at how closely the district represents a circle, and by looking at the compactness, we can judge this based on a number of how often you can draw a line between 2 points in the district and it stays contained within the district. Second, we can use the Monte Carlo method that compares the proportion of votes to the proportion of voters after the fact of an election, and comparing to that how voting could have changed the results. Finally, we can look at the efficiency gap. This was used in the North Carolina Supreme Court case to judge if gerrymandering occurred. It was developed by Stephanopoulos and McGhee. It looks at the difference of wasted votes compared to the total. A wasted vote is any vote going to the losing party in a district or any vote more than the majority of the winning party. This is accurately named because it represents what many people believe is a wasted vote and why many people agree to not vote in elections because they think if they're voting for the winning party, then what was the point? Because they already won. And if they vote for the losing party, again, why did they vote if they were just going to lose? If we look at the images on the page, they represent states and voters. We can see how the efficiency gap works out. The stars are party A and the blank spaces are party B. If we look at plan 1 in red, the wasted votes for each is 9, so when we subtract that from each other and divide by 42, we get an efficiency gap of 0%. And this is the ideal outcome that we want to see when calculating the efficiency gap, as it shows that no party sway has occurred. In plan 2, the green, we find the wasted votes we get for party A has 1 and party B is 15. So the difference of those is negative 14. And when we calculate the efficiency gap, it comes out to be negative 1/3, suggesting that there's an advantage for party A. The efficiency gap works by if there's a large negative value, it calculates for party A. If it is 0, there is no party sway, and if it's for a large positive number, it is for party B. We are going to use the efficiency gap to test my own algorithm that redistricts a random state. The district in purple is representative of what I hope to do by packing all of the districts equally, because I have equal voters in each district and each party. It will come out with an efficiency gap of 0 like this purple state does, because they equally are wasting the same number of votes. For this research, I wanted to create a randomized state divide into electoral districts with no human input. I began by setting up a state that had 36 citizens with equal party distribution of 18 in each party, and that would create 4 equal districts. I used an array to assign values that represented their party and then had a random number generator mix it up. I had the values of 1 equal red and 2 equal blue. You can see below how those were printed onto a map of the state. I began with 3 baseline algorithms of my choice based on geometry to get an understanding of the average efficiency gap that each would produce so that I could compare my own algorithm to it. I ran each of the algorithms 5,000 times in total in order to get more reliable results for comparison. For the first graph on the left, I simply split the graph down the center both ways, and this created an average efficiency gap of 8.77% and had unique values of 0% and 27%. These appeared approximately 68% of the time and 32% of the time. The second map, which divided them in a similar but different way, had an average efficiency gap of 8.9% with the same unique values of 0 and 27 with just slightly different frequency rates. My final test was to split them up by putting the first 9 values of the array in a group, then the second 9, and so on. This had an average efficiency gap of 10.98% and produced unique values of 0%, 5%, 22%, 27%, and 33%. This is very different than the other 2 algorithms that I ran. I'm looking into the theory behind why these values are specifically showing up and why others are not. The values in the last program correspond to a difference in wasted votes of 0, 2, 8, 10, and 12. When I began playing with my results, I found that it was impossible to get a difference of wasted votes with the value of 4 or 6 without changing the equality factor of the population of each party. In order to get those, I would have to change it to 18 and 20 or something similar. I'm looking further into mathematically proving this hypothesis and getting more answers. Now that I have this baseline, I want to create a smart algorithm that would create the district on its own by comparing the parties of each person with one another in order to choose its own districts. This way that no human bias can take place. It was a smart algorithm that I developed that would redistrict a state with no input. The algorithm starts in the bottom left corner at the index of 0 and begins by comparing the values up, right, down, and left in that order. It does this by adding 1, 6, subtracting 1, and subtracting 6 from the starting point. The first time that it finds a value that is similar when doing the addition or subtraction, it adds that value to its district, which I coded as an array, and it updates the current position to the index of the one that was just selected. This one then repeats the process until there are 9 chosen within the district. Then it begins at the next lowest array index value or person that was not previously chosen. There are many rules that stop the algorithm from picking the same value twice, picking one that was used in another district, or one that is outside of the boundaries. The hardest part about this was ensuring continuous districts and defining code with what a cutoff point was and how to add it to a district when this happens. The map below represents just one possible outcome that happened with my code. You can see how the districts are continuous and how they were slowly formed with each other by not picking points that were already chosen. This map is created and printed from my results, and it was printed many times for all 100 times that I ran the code. I used these values to come up with an efficiency gap for each, and then I found the average. The average when I ran this was 8.37%, which is relatively similar but still smaller than the values from my baseline. I still had unique values of 0 and 27.7%, and they had a similar frequency of 67 and 33% of the time. I am looking to begin changing this code in order to hopefully get an efficiency gap with a smaller value and complete more test runs. For my future work, I hope to run this on a larger sample state, such as one with 81 members and 9 districts, or with a different setup, such as not equal values, run it on a less randomized map, and one that reflects more patterns similar to real life, such as large cities and rural states, and how voter populations are typically found in the real life with those areas. And finally, I want to attempt to use this code or something similar to redistrict a real state using the individual voting precincts as my points of comparison between each other.